Path compression in disjoint set. Path compression is a technique used in disjoint set data structure in order to flatten the tree during find operation. So when you flatten the tree, what is the advantage you are going to get? You are going to improve the performance of find as well as union operations. So let us see how this is done. In the previous two lectures, when we discussed in detail about disjoint set data structure, we learned that there are two primary operations that we can do on disjoint sets. First one is find operation and the second one is union operation. So in the initial lecture, when we discussed about find operation, we had seen that it took order of n time, and what about the union operation? It also took order of n time. But with the introduction of union by rank, concept, we were able to improve these efficiencies and we were able to bring down the time complexity to order of log n. So from order of n, we brought it down to order of log n using union by rank technique. This time, using path compression technique, we want to bring it down to a constant time. This is our final aim. Okay. So let us see how this path compression works. Normally, let us say you want to do some find operation. So when find is called, let us for some element x, what are you going to do? You are going to traverse from x till the root of the tree. So if this is your tree, if you have a tree like this, and you called, let us say, some find operation on this node, what will you do? You want to traverse from this node till the root of the tree. This is what you are going to do. This means anyway you are going to travel from the node till the root. During this, if you do one particular operation, you can improve the time complexity of all the future operations. And this is whenever you are traveling from that node to the root during a find operation, you will take each of the nodes that you see in the path and you will attach all of them directly to the root. So using this technique, what happens is next time when you call find for any of those nodes which are part of this root, you will be able to do in order of one time because those are directly attached to the root. First, let us draw this and understand because that is the easiest way to understand this technique. Let us say you have a tree like this. You have 5. From 5 you have, let us say, 4 and let us say 3, 2, 1. Let us say your tree is looking like this. And on this side, let us say you have 6, 7, 8. If this is your tree, if I call find operation on 1, what will happen? From this 1, I will start traversing each node up till the root. Finally, I'll reach the representative element which is having value 5. What will I do? I will say 5 is the final result of my find operation, which means while doing find, I am anyway traveling from here to there. So during this, I'll do one more thing. Whenever I see any node, I'll keep that node and I'll attach it to the root that I'm going to find. So let us say I called find on 2. If I do find on 2, I will see 3 on the path. What will I do? I'll take 3 and I'll directly attach 3 to the root. So 2 is where I started. I saw 3, so I attach 3 to the root and then I saw 4. 4 is already attached to the root. So what happens? This 2 will also get attached to the root. So now if you see my tree, almost all the elements are directly attached to the root. You understood this, right? See, from 4 there was 3, 2 and 1. What did I do? I travel from 2 till the root. So whichever node I found, I took that node and I directly attached to the tree. So 4 is already directly attached, so I don't have to attach. 3 was not attached, so I attached 3 to the root. 2 also I am going to attach to the root. So 2 is also attached to the root. 1 will stay as it is. So this is how path compression is used. Whenever you are traveling from one point to the node, to the root node, in order to do a find operation, you will take all the nodes that you see during the visit and you will attach everything directly to the root. So next time, if I call a find operation on, let us say 3, I can directly say it is under the root 5 because 3 is directly attached to 5. So it becomes an order of 1 operation. Let us say I did find of 7 now. What will happen? I'll start find from 7. I'll travel up. I'll see 6 is already attached to root. So I'll take 7 and I'll attach it to root. So in this case, you can note that a single node may have any number of children. So this is how disjoint set data structure works. So after this path compression, all nodes that are in the path will be able to do a find operation in order of 1 time. So now if you see 2, 4, 6, 3, 7, all of these are directly attached to the node. So whenever you perform a find operation, you will be applying path compression. So what are you going to do now in disjoint set? Whenever you do find operation, you will do path compression. Whenever you do a union operation, you will do it according to union by rank rule. So if you follow both of these, if both of these are followed, then the time complexity of both find as well as union operation will come down to order of alpha of n. Both of these will be order of alpha of n. And what is this alpha? Alpha is inverse Ackermann constant. What is inverse Ackermann constant? Inverse Ackermann function. What is inverse Ackermann function? This is a function with a lot of specialities, and the main one is that it grows so slowly that even if you take a very large number and put it into inverse Ackermann function, you will get a very small number like 1, 2 or 3. Even if it is such a huge number, you will get a very small number because this inverse Ackermann function grows very slowly. Why does it give such a small number? Because Ackermann function, this is a function which grows rapidly. That is, even if you take Ackermann function of 4, then A44 will give you a very large number. So it is something like 2 power, 2 power, 2 power, something like this, 6, 5, 5, 3, 6, something like this is Ackermann function. So even if you give a number 4, it is giving such a large value which is incomprehensible, right? If you actually write this complete number, you won't even manage to count the digits. It is such a large number. So if this is the situation with Ackermann function, what about the inverse Ackermann function? In inverse Ackermann function, even if you give this number, which is such a large number, even if you put it here, still the inverse Ackermann function will give you number 4 because it will give you the reverse of whatever Ackermann is doing. So because you are having this inverse Ackermann function here, you can treat it as a constant only, because even if the value of n is extremely large, something like this, still this inverse Ackermann function will give you a very small number, because of which you can consider this as constant time complexity. So what did you learn? By using path compression and union by rank techniques, if both of these are applied, then in disjoint sets, find operation can be done in order of alpha of n, which is constant time, and union operation can also be done in order of alpha of n, which is also constant time. So from order of n, we brought the time complexity down to order of log n using union by rank concept, and then now with the help of path compression technique, we are able to bring it down to constant time complexity. So this is about path compression in disjoint set.